Okay. Well, yeah, let me share my screen. Okay, so I'm gonna basically just go through this document from the O book that I expanded. I think Sean had written a lot of the original version. Maybe Nico and Nicole also, but I tried to kind of expand it and really put in a lot of the technical details for how these things work. And that turned out to be really useful because I kind of clarified some things for myself that I knew we had to have certain kinds of axioms, but I couldn't remember why. So hopefully this explains all of it. And if feel free to ask any questions while I'm going through it. And also this sort of a draft. So if some things can be moved around, or if we realize like I forgot to talk about something in here, then I'll try to add it like soon after this meeting. So yeah, this is the guide to taxon restrictions. And so what is a taxon restriction? So it's just a formalized way to record what species or what group of organisms a term applies to. And this is something that's important even in multi-species or species neutral ontologies. Just as an example, Go, which covers, doesn't focus on any particular species, but it has terms like lactation, which is a process, and that only occurs in mammals. And so it's nice if we can have that formalized and checked by the reasoner as we're editing the ontology. And so what are some of the uses for taxon restrictions? So like I just said, one of them is finding inconsistencies. And so the way we use them in OBO, we use the NCBI taxonomy ontology and reference those terms in our taxon restriction statements. And so this kind of relies on the one part of the taxonomy ontology is that all the sibling taxa are stated to be disjoint, so nothing can be insect and rodent at the same time. And so when Go first implemented taxon restrictions, it uncovered almost 6,000 errors in the ontology, according to this publication. So that's linked there. You use the same logical approach just to define a taxon-specific subclass. And so, if you have a anatomical structure like clavicle, you make a new a subclass that's the specifically the human clavicle. And you just define that with an equivalent class expression, like here. Human clavicle is equivalent to a clavicle bone that's in taxon Homo sapiens. And so in taxon is kind of the core property that's driving the logic. And we'll talk more about some of the other properties, but that everything's kind of based on this. And so a couple other things you can do when you have taxon restrictions in your ontology, you can automatically create a taxon specific slim. You can use the reasoner to generate an ontology subset that only has those terms that are logically allowed within a taxon. There's some different tools that implement this. Like it's implemented in the old OWL tools program, but basically it puts in an assertion that everything in the ontology is in the taxon you care about, and then it finds out which classes now become unsatisfiable, and then you just delete all of those. So it may leave some that still aren't appropriate for your taxon. It just depends on how comprehensive the taxon restrictions are. And then you could use it for querying, query all the terms that are known to be, in some particular taxon. Again, it kind of depends on which, how comprehensive the taxon restrictions are, and maybe some terms that you might want to find are not really restricted, even though they're allowed in a taxon. So those are the queries like this. Could be incomplete. It all depends on your data. And so, I just saw the comments in the chat. And so, yeah, I'm looking at this version in my pull request. I was just going to make a few more edits after this maybe, and before kind of merging it into the book. So this is on a branch in the repository. So there's kind of three main types of taxon restrictions that correspond to some different OWL properties. And so, given some class C, or something we care about like an anatomical entity or biological process, we kind of have some different categories. So there's like the all-in restriction, which you might say C in taxon T. T is the taxon. So this is a statement saying like hair is found only in mammals, where all instances of hair are in an instance of mammal. Another one is a never in or not in, so C never in T would be a statement like hair is never found in birds. So that way, if you ever create some logical construct or make an annotation that's linking a hair or some type of hair to something that's a bird, you'll get a logical error. And then the sum in restriction might be like, I don't know if you don't run into this quite as much because I think we kind of implemented the logic more recently, but they're just saying that C is present in taxon T. Actually, I think sometimes people think that the first all in actually works this way, but this is just saying like hair is found in skunks, hair is found in whales. Like you're just kind of making a statement that like there is an example of this structure present in that taxon, and this is useful for quality control because even if like pretend we didn't know the taxonomic extent of hair, we can at least say some of the taxa that we definitely see it in, and that way, if some other taxon restrictions get added to the ontology that would make it impossible for hair to be in whales or something, then the presence of this would give us a logical error, which would be useful to catch. And so the next section here kind of is a bit more detail about the logical representation, although now that I kind of finished the rest of the document, I might make some edits to these because so it kind of goes through each one in a way that I sort of talked about, for the all instances of C or in some instance of taxon T. So it's a little bit more explicit. But this does kind of raise the point that the name of this property in taxon is not really a great label. It really should be like in the organism, because an instance of a taxon class is an individual organism. So you're not really relating like to the taxon. You're just saying that if they have an instance of hair or whatever, it has to have an in-taxon relationship to some instance of mammals. And so that's a particular organism. And so generally we put these in the ontology just by using this standard like existential relation. So C is an in-taxon some T. And then I skip a little bit of this here because I have more detail later. Not in is kind of covered already. No instances of C are in taxon T. So if something is in taxon T, it can't be in the class C. And so there's sort of a basic logical representation for it, where it'd be something like not in taxon some T. So it's very similar to the expression here, but it's just the complement of that. But to make this really work with ELK, we have to add some sort of helper axioms. And there's a lot more detail about that down below. So then a sum in assertion saying that there is at least one instance of C that's in taxon T. And so there's a couple ways you could, in your ontology, create an individual like this individual A and say it has the type C and in taxon T. So that way, if you ever added some other restrictions that made that impossible, then your ontology would become inconsistent. But there's another way you could do it is by generating a class that's equivalent to that expression, and then just that class would become unsatisfiable. This is sort of like a generated only for QC purposes, though. This class. let's see. So getting into a bit more of the details about how these work. As it has been saying, one of the main applications is finding logical inconsistencies. And so when you start connecting obo-ontologies together, in a really complicated way, like the way, Ubron and Cell and Go and Kebi and what all these, they all reference each other in different ways, and that gets kind of complicated. And so, certain cell types are only in certain species, and certain processes are only in certain species. And so we want to make sure we don't connect, two terms together that really could never be related to each other because they're never in the same taxon. And so the taxon restrictions help us kind of manage that. But it's really to kind of know mentally how they're going to apply. It's good to think about how they propagate in the ontology and look over the class hierarchy. So an in-taxon restriction is going to also apply to all the superclasses of the taxon and all the subclasses of the subject term. So let's just say you have this ontology that says whisker is a subclass of hair. And we have a really simple taxonomy that mammals are a subclass of tetrapods. So if you have this one taxon restriction, hair is in mammals, then all the dotted lines show you, all the kind of implied in taxon statements from that one. So all the subclasses of hair. So if you have a term whisker, it also is in mammals, has to be in mammals. And then kind of up the tree for the taxonomy. So if hair has to be in mammals, then every hair also must be in a tetrapod, and every whisker must be in a tetrapod. And so, but it's the part of that, let's see, changes when you, let's see, notes for never in taxon, it's still subclasses of the subject term, but it becomes subclasses of the taxon. So we have salon or whisker again, and then we have some subclass facial whisker. So let's say there's an assertion that whiskers are never in hominids. So I read in Wikipedia that no great apes have vibrissae. So if whisker is never in hominids, then all its subclasses, same thing. Facial whisker is never in hominids. But it also applies to all the subclasses of hominids. So whisker is never in Homo sapiens, and same for facial whisker. So that's kind of how the nevers propagate sort of the opposite direction in the taxonomy from the previous example. And so the present in taxon are even like slightly different. So it's superclasses of both. So if we say whiskers are present in cats, and that's our assertion, that applies to all the superclasses of whiskers. So definitely hair is present in cats, and also applies to all the superclasses of the taxon. Whiskers are also definitely present in carnivores, and hair is present in carnivores. And so hopefully these are like a helpful way to kind of informally keep in mind how these things propagate over the ontology. And so another way that taxon restrictions get propagated through the ontology is through property chains. And so in RO, there's a number of property chains defined for in-taxon. And just as one example, it propagates over part of. And so this is a property chain, which means like, if something is part of something else and that thing is if something is part of something else and that thing is in taxon, some taxon, well, then the first thing has to be in taxon, that taxon. So all the parts of the thing are also in the same taxon. So as an example, back to whiskers again, we have a whisker muscle, which is part of a whisker. And so we have two taxon restrictions in this ontology. Hairs are part of mammals, and whiskers are never in hominids. And so we're going to propagate both of those over the part of, and so, whisker is a subclass of hair, so it's also in taxon mammals. And then because the muscle is part of the whisker, then it has to be in taxon mammals. And so then we kind of propagate the same effects down for the never in taxon. So whisker muscle is never in hominids or Homo sapiens. And so property chains, I think, are really good to think about because they're the most common way in which taxon restrictions propagate across ontology boundaries. Like this happens a lot in gene ontology. It references a lot of Oberon terms for biological processes, like where they occur or what they produce. So there'll be different kinds of processes in Go that are like developmental processes that result in the development of some structure. So there's this relation results in developmental progression of, has a property chain within taxon as well. And so whatever taxon restrictions are in Oberon on those terms will then apply to all the processes that relate to those anatomical structures. And so I just keep in mind, like these drawings are kind of informal, like I think they're logically correct, but they're not exactly OWL. They're kind of knowledge graph style. So the never in taxon and present in taxon are actually annotation properties that we translate into more complex logical statements that are all based on in taxon, which I mentioned above, like the never in taxon is actually like not in taxon. Okay, so the next section kind of gets into the real details of everything you really need to have present to make these work. And this is the part that was kind of really useful for me to write down because there were different pieces that I knew you needed to be there, but I kind of forgot sometimes the exact details of why. So a lot of the complexity comes from the fact that we're trying to make this work with the AL-EL profile. And so that AL-EL is a subset of AL, which it's possible to write a faster and more scalable reasoning algorithm for, because we're not allowing you to use all of the language features, only certain ones. And so probably a lot of you use the ELK reasoner and Protege to develop like gene ontology or Mondo, these kinds of ontologies. ELK is really the only reasoner that really is scalable enough to deal with those in Protege. And so we want to make all of this work with ELK because that's what we're using in our QC pipelines. I'm using in Protege. And so I do have some comments in here about which constructs work with Hermit, which is sort of the complete AL reasoner, which I think just helps to know like why we can't use those features. And so there's like a little bit more complicated ontology, but it has enough stuff in it to kind of go through 3 different examples. And so we have whiskers. Whisker muscle is part of a whisker. It's a type of muscle. Whiskers are types of hairs. So that's kind of the anatomy. And then we have humans under mammals, and we have Siluriformes are catfish. And teleost fish, tetrapods. So the only place where we have a disjointness in the taxonomy is right here, because all the others we don't have. I didn't write down any of the sibling taxa. And so these 3 terms here are kind of like examples of terms that someone made by accident or incorrectly, that we want the reasoner to find that they're unsatisfiable. Maybe somebody used the term whisker with humans, they were kind of thinking of mustache or something. Whisker and catfish, they mixed it up with barbels or something like that. So just before we get to the details, like why do we think whisker in human should be unsatisfiable? Well, this is a defined class that's, a whisker that's in taxon Homo sapiens, but it is a type of whisker, and a whisker is, it says never in taxon hominids. So that's kind of you can kind of see that conflict immediately. So whisker and catfish, it's like a whisker, and so it is a hair, and so it's always in mammals. But this term, this whiskering catfish, is in Siluriforms, which is a teleos, which is disjoint from mammals. And so, yeah, if something is in, it has to be in mammals, and it also has to be in teleos. That shouldn't be possible. So then whisker muscle in human, this one should be unsatisfiable because it's a whisker muscle. So it's, let's see. Yeah, so it's part of a whisker, and so it inherits this never in hominids, but we're saying that it's in humans. So that's a never in over a property chain, which is sort of the most complicated reasoning that we have to do here. So we'll just start adding in like the actual logical axioms we need to make it work. So for we have two taxon restrictions that are in the ontology here, right? So this one, whisker never in hominids, and hair in taxon mammals. So we can write that. Hair in taxon mammals, we have this axiom. Hair is a subclass of in taxon some mammalia. And for the never in, we have whisker subclass of not in taxon hominidae. So let's see if like just this modeling is enough to make this work. So actually, both hermit and elk can derive that whisker in human is unsatisfiable just from having these in the ontology and the taxonomy. And so these are the axioms. If you ask protege for the explanation, it takes, combine these three axioms and you find that whisker in human is unsatisfiable. And so you can see, in taxon Homo sapiens, not in taxon hominidae. But neither reasoner can find the other two problems. And so if we just focus on one first, whisker and catfish, the reasoner infers that it's in taxon both mammalia and Siluriforms, but it doesn't think that's a problem. So both reasoners can figure that out. And so it's not a problem because they're like mammalia and Siluriforms are disjoint classes, but there isn't anything in ontology saying that you can only be in one taxon at a time. And so the first way that someone would think to make it only possible to be in one thing at a time would be to make in taxon a functional property, which is a functional property means you can only have one value, one object for that. But we can't do that for two reasons. So since we want to have all these property chains for in taxon, Al doesn't let us combine those features together, just this really like esoteric limitation. And so that prohibits us from making it a functional property. But anyway, functional properties aren't part of ALEL, so it wouldn't work with elk anyway. So one way that we could make it work works for hermit, but not elk. We could add, for all of our always in taxon restrictions, in addition to saying hair subclass of in taxon some mammal, we could say hair subclass of in taxon only mammal. And that's sufficient for hermit to detect that whisker and catfish is impossible. But it's not good for elk because the only restriction doesn't work in ALEL. So instead of adding this, we don't need to add this at all. In the taxonomy ontology, we generate an extra disjointness axiom for every taxon disjointness. So where we have tetrapods disjoint with teleostei, we also generate this GCI. In taxon tetrapods is disjoint with in taxon teleostei. And so this is a disjointness with an expression on both sides. And so if you have these, which you have to generate programmatically for the whole taxonomy ontology, and so that works for both hermit and elk, now they can find that whisker and catfish is unsatisfiable. And so this is the explanation from elk. And so we still can't find that whisker muscle in human is unsatisfiable. And that is a little bit more complicated than the others because it requires like interacting a property chain with a never in taxon assertion. And actually this wasn't working for a long time. I just realized last year that this didn't work. And so it's new information here. So if we could have made in taxon a functional property, like just to mention that again, Hermit would be able to figure this out. But as we said before, we can't do that. So there's the solution for Hermit also works for elk. And so in combination with the extra disjointness we just added up here, we add another, let's see, another disjointness axiom. For every taxon in taxonomy ontology, we say in taxon hominids disjoint with in taxon some not hominid. And so actually I need to change this because this is enough for Hermit, but to make it work for elk, we also need to expand our never end taxon assertion. So up above, we translated our never end taxon into this whisker not in taxon hominid. But we need to add to that every time we translate one of those. We need to add whisker in taxon some not hominid. And so this is sort of has to be added to your never end taxon expansions. And so now both with that, Hermit and elk find whisker and muscle and human unsatisfiable. And so just to summarize all of that, like so that we can keep straight, what we need in every ontology QC pipeline to make all this work, you need the property chains from relation ontology. For the taxonomy ontology, you need like 3 kinds of disjointness statements. So this can all be generated ahead of time and downloaded from taxonomy ontology. And then for every in taxon, it's just straightforward. You just put this in your ontology. And then for every never in, you need to expand that to both of these statements. So that kind of is everything needed to make it all work. And so actually this kind of recaps what I just said, just saying how to do it. You can download the taxon disjoints within this file, although it's only for a subset of the ontology. And also it's currently missing that like latest disjointness that I just sort of discovered last year. So we need to expand the NCBI taxon pipeline, I think, to kind of have all the disjointness in it that's needed. Right now in Go, we're generating this with a Sparkle query. And then you have your own taxon restrictions within your ontology. And so you're all in, don't require any expansion. And then if you're using the shortcut annotation properties, one thing you could do, you could use robot expand, the command, to generate those logical forms, before you check for unsatisfiable classes. So, yeah, hopefully that was possible to follow. But it was really useful, I think, like to write all that down because some of those things I kind of had bumping around in my head, and now it's all down in this doc, so we can kind of make sure it's all true. And so, kind of to shift topics, sort of, if you have taxon restrictions in your ontology, and let's say you have all your imports set up right, so that they work, how can you explore them in Protege? And so one simple way that doesn't require any extra plugins is just using DL queries. And so if you have this works if you're wondering about a particular taxon. So let's say we have some term whisker, and somebody asks us to add a taxon constraint. Whiskers are in mammals. And so one thing you can do is just see if that already is implied by anything else. So you do a DL query for whisker and in taxon mammalia. And so there's a few different possibilities in the result. So if the equivalent classes includes al nothing, meaning that expression is unsatisfiable, then you know that there's a never end taxon that holds for that taxon and that term. If the equivalent classes include the term itself, like if this expression here is equivalent to whisker, then you know that there's an in taxon in effect, that whiskers are always in mammals. And then if the term of interest like whisker is just in superclasses and there's not, it's not unsatisfiable, then there's just no particular, there's no taxon restriction for that term in that taxon. So one more, something that you can do that's like a bit more comprehensive is use this Taxon Constraints plugin for Protege. And so there's a link here to the repo, which has information on installing it. Like it's available just in the plugins list in Protege. And so this lets you turn on the reasoner and then just see exactly like what are the most specific taxon restrictions that are in effect for a term. And so I can run it real quick. This is something that I wrote a couple of years ago. But let me share. Okay, is Protege visible now? Okay, so just example, this is the Go edit file. And like we have this term marginal disk development. And so I've turned on the reasoner. I can, well, and just to show you what I meant with the other things. So let's do this first. Marginal disk development and taxon some, like let's like if you pick arthropods. All right, so I turned on equivalent classes. And so you can see that this expression is equivalent to the term itself. And so that just that tells me that imaginal disk development is always in arthropods. And so if we had put something here like, let's go. Mammals. So now that expression is built into nothing. So we also know it's never in mammals. So I'm going to switch over here. So to get the I have the Taxon Constraints plugin installed, and so you probably can't see my menu, but I go into Window and then Views, Obo Views, and then Taxon Constraints. And so one thing is I always leave it. It's a bit slow, so it's hard to navigate around the ontology if you have this panel. And so I just click to add it, and it's going to take several seconds because it does like thousands of queries to the reasoner. Okay, so now it's done. And so now you can see, so it has two sections, always in Taxon, never in Taxon. You see this one up here, arthropods. It's not yellow because that's a directly asserted taxon restriction. So that's right here. But the yellow ones are what the reasoner has inferred. And so it actually infers that it's always an insect. So that's more specific than the one that's here. And that's coming from some other terms that there must be. So this says like results in development of imaginal disk. Probably Uberon says that that's only in insects. And so this is kind of inheriting that more specific one, which is still compatible, but it's just making it even more specific. And then the never in taxon, usually you're going to have a list of taxa here because it's sort of like it's the non-redundant, like most specific set of taxa that this can't be in. Because basically whatever the common superclass is of all these taxa is probably also the superclass of arthropods or something. So that's how the plugin works. And you can, to understand why in any of these things is inferred, you can hit the question mark and get an explanation like normal. And so I think this is really useful. The only issue is that it's just like a little bit slow. And so usually I just open it once I get to the term I care about, and then I close it again. So let's see. Seeing mammals and never. Let me go back. Sierra has a question about seeing mammals, and I'll explain that. Gotta wait a few seconds again. So it is never in mammals, but it's right. So you can see here it's never in deuterostome. So each of these is going to be as broad as possible. So it's kind of the minimal set. And so mammals is a subclass of deuterostomes. And so it's just like it's that term and everything below it. Otherwise, this would be like, you know, thousands and thousands of terms. So it's the kind of minimum set these would be at the broadest level, and this is going to be at the most specific level. Just because of going back to the way that things propagate. All right, and so then there's a link here to adding taxon restrictions to Protege in a different document. But I just remember there's one more thing that I kind of forgot to mention that is up here in this types of taxon restrictions statement. There's a little note for each one. So for all in or always in restrictions, if you're adding an always in restriction to the ontology, you should make the taxon as specific as possible. Well, but it still needs to be correct. Like, so like for the imaginal disk development, we added like Go has always in arthropods, but actually we could make it always in insects, and that would still be true. But you can't, you know, if you go any more specific than that, then it's going to be wrong because it's like not always in beetles or something, because it's also in other insects. And so this one, it's good to be as specific as is true. Now then the never end ones, you kind of are trying to go the other way. You want to make it as broad as possible. Like if you know that some process like never occurs in brewer's yeast, you could add that. But if you kind of also know that really it's never in fungi at all, then that would be better to add that. So make the never end ones as broad as you can. And then for the some in statements, just make those as specific as possible, because they're kind of more like observations. And remember, they propagate to superclasses on both sides. So, you know, you say like hair is present in striped skunk, you know, and hair is present in dolphins, or whatever, something like that. So there's just some guidance on like how to think about which taxon you're putting in. So, all right, that's the whole document. And does anybody have any questions or comments on kind of reorganizing anything or anything like that? So, Sabrina?
Yes, hi. Thank you so much. That was great and very, very helpful. You probably said all the information I need to know, but my brain is not connecting things. So can you use taxon constraint for classification? Let's say in Mondo, I want to create a class that is, let's say, diseases in dogs. And so I could add some taxon constraints saying that all the diseases classified under this class is, you know, is present in dogs. We can go as deep as it's only in dogs, or it's only in dog and in some dogs, but you know, let's not go there for now. Just like, you know, so if I have a class that has a taxon constraint and I run the reasoner, will I expect that some terms will be reclassified under that class, or is it a bit too complicated and therefore
you sort of can, like, because if you made an expression disease and in taxon dog, you would get as subclasses all of the diseases that were always in dogs or that were only in dogs. But if you had some disease that was like can be in dogs and can also be in cats and humans, then that won't be a subclass of in taxon dogs. Like, and it's not, and like directly in OWL, like it's not really easy to query like for diseases that have an instance in dogs. Like maybe like a different, it would just be like a different query. So I think it would be kind of incomplete, like, because yeah, you can definitely classify things by everything that's always in some taxon. But I feel like you also want to, I think you're also asking about the things that can be the taxon, and that is like a little trickier to do with owl classification. And so I don't know if Nico has like a suggestion. I think you have a different question, but do you have any other ideas about that, Nico?
No, not right now. I have the question in my head, so I didn't think it through, to be honest, right now, but it's definitely an important thing we should sort out.
Can I ask a follow-up question? So if I have the axiom that says in some instance of dog or whatever, and then I query for only in dog, is it will I? Oh, okay. Let me rephrase the question. I want to query for, let's say, diseases that occurs in dogs, and it could be in other species too. Will I also find the diseases that are only in dog, or will it be very specific to can occur in some dogs? Does it make sense when I'm talking?
Yeah.
Okay.
I think it's kind of, well, if you had, it's sort of, I think it has to be sort of application driven. You kind of have to set things up. It may not be that easy to do just looking at your ontology and protege. Like let's say you had, okay, hair is only in mammals, and you had something else that was like, okay, lungs are not only in mammals, but lungs are found in whales. And so that could be like if you expanded it into these classes, where you'd have like, this would be like whale lung, some generated named class. Then you queried for like everything, okay, that's in taxon mammal. You would get, everything in taxon mammal, you'd get this class like whale lung. You would need kind of like an outside of logic way to map that to lung. Like, it's totally doable, like in a system that somebody's building. It's just not, or if you just saw that and you knew that, oh, this is a generated lung class, like if you had these in protege, you could kind of do that mapping in your head. But it wouldn't be the lung class itself, it'd be this special subclass. So I don't know if that's like really clear, but I think what you want to do is totally doable. It just like takes some setup.
Okay, great. Thank you.
Mika?
Thank you very much. First of all, this was super awesome. And so I have more like two empirical questions. So in your kind of experience with, you hinted at the fact that, adding taxon constraints, which is, right now we have no good way to measure like how dense and how correct our taxon constraints actually are, whether we are severely underspecified, whether we are quite good or not. But how often does a taxon constraint added in Uberon or CL or something like that cause a red flag going up in Go and asking a Go curator to actually change stuff in Go? That's the first kind of part of the question. And the second part of that same question is, what is the normal response from the curation side? Is it to drop, or is it most often the case that the axiomatization is going to be relaxed as a response to such a situation? So basically, our Go curators then seeing, yeah, maybe I shouldn't link to this Uberon term, and they are dropping this constraint from their axioms? Or will they, for example, reconsider placement of the Go process? So is it really going to change classification of biological processes or even cellular components or something like that in response to this change in Uberon?
I think both of those have happened. and like fairly frequently. It's hard to say like, exactly like how often it happens, but I think taxon constraint issues kind of coming up on the term tracker as something for the editors to deal with it's not like constant, but it's definitely frequent enough that like it's a normal thing that they need to deal with, like maybe every several weeks or something. So there's been several examples, I think, of Go processes where maybe they kind of realized something was a bit too human oriented or vertebrate, assuming something about vertebrates, and then mapped it like, well, there's just one that we talked about yesterday about the endocrine system, which I didn't fully follow all the physiology, but there's an issue going on right now coming from CL and Go trying to figure out like if these, how specific these endocrine system processes are supposed to be. But yeah, so I mean, I think it does happen like pretty frequently. We started adding the present in taxon. We have a few statements like that because there was a heart process in Go, which had kind of inadvertently gotten connected to vertebrate hearts, but it was really meant to be like more generic, and Drosophila folks were using the term in annotations, and then like something happened where that inconsistency got detected, and so that's where you can like, if you have some, let's say we have some like heart contraction or something, and we don't really know that it's taxonomic scope, but we want to just make sure that it always works for flies and doesn't get inadvertently made into a vertebrate specific term. We put that present in taxon statement in and just say this is present in flies. And so then if any connections happen in the ontology that makes that heart contraction thing suddenly become vertebrate specific, which is like not that hard to do, like based from all these connections to Ubron, that'll get flagged. So I think we could go a lot further with the present taxon stuff, but I didn't have anything about present taxon in this QC section. Like maybe, well, I guess I had right there, but as far all the reasoning parts, I didn't. But it's
so
kind
this is excellent. So I just because there are also many many people here in this call that are actually contributing actively to Uberons. I just want to say that this is a really nice, a really great picture that you've drawn here for us for how actually taxon constraints and careful curation of taxon constraints on the side of Uberon actually helps when curating downstream ontologies for catching errors and stuff. So this is an important message that sometimes is maybe not so arrives so easily in our minds, because for us we don't really know exactly how these we think of mostly of Uberon as our ontology, right? Like not ontology, our anatomical entities linked with each other, but the fact that these constraints are being created and used for QC by downstream ontologies, I think is another really good thing that for us to understand about the value of doing this right and doing it thoroughly as well. So I just wanted to point that out in response to what you just described. So thanks for that. So I want to see if there's anyone else who wants to ask a question, then they should go first. But I have another one if there is no other person who wants to ask something. All right. So then so basically this is again a bit more going into knowledge graph land from what you've described here. So I wonder what your opinion is. So basically we curate these like never in taxon, present in taxon, and in taxon links between our the anatomical entities and the taxa they occur in. Do you see any kind of benefits of treating these kind of links direct links, whether they are on the way translated into OWL and used for quality control and so on to the site. But do you see any value in these links for applications? So do you see that there's value in these annotations for their annotation's sake? So I'm thinking of things like including additional edges in knowledge graph, which actually, for things like vertebrates will create maybe like hugely connected links, hugely connected nodes and stuff like that. But do you see any value in making these things for like knowledge graph kind of applications or downstream applications, like propagating these direct links out as well? Or do you really see the main use case to be in the quality assurance and classification use cases?
No, I mean, I always feel like it's always useful to be able to see things everywhere. So I don't see any reason not to have like a knowledge graph kind of output. And some of the downstream Go users have been asking, I think they would like to see some of the taxon restrictions more clearly, because they don't use Go plus, like they use like go.owl, where all these they're filtered out anyway. And then or they aren't really using OWL like this, and so they'll just look at the Go, or they look at Go plus, and they'll just see the taxon constraints like that we assert in there. They don't really realize like all the ones that come from Uberon, because that only happens when you have like all this logic set up and you're using an OWL reasoner. And so we talked a lot, and like I haven't really gotten to it, about like kind of pre-computing all these consequences and asserting them in an easy to read way. Like we do have one thing like that, which is this kind of matrix that I generate that's sort of like Go terms by taxa, and then it's like a bunch of zeros and ones, which is just, I think, or zeros and ones are blank. It's like if it's a zero, then there's like a never in taxon that holds, and if it's a one, always in taxon holds. But they use that output in the Panther pipeline. So it's kind of specific for that. But I think like these kind of drawings up here, like, we could compute. There's a bunch of never in taxon edges and in taxon edges. Like, you can add this to Ubergraph maybe. Like, it's just a little different from what we have now, but especially because it's a bit weird, like the never in taxon kind of propagates a different way, but than a normal existential restriction. But
so just for this particular idea, just imagine, let's say you're a curator, right? And you use OLS to pick a term. And in the first instance, you're looking at a term, you may not understand real quick that let's say, for example, a specific term is or limited to specific taxons, or is frequently associated with specific taxons. So if you think of kind of like either like a browser that allows you to say, give me only the terms pertaining to taxon XYZ, so that is doing on the fly taxon restriction slimming in a, let's say, OLS kind of search interface, or on the other side, just simply saying, okay, this is the term, and there is like a box on the side that just says like it doesn't appear in this and this and this and this taxon, which may help a curator, for example, to understand, okay, I shouldn't use this particular term in this context that I'm right now in. The label made me think it may be applicable, but actually this term is not applicable for this particular curation use case.
I think pre-computing all these things, and like if they were in Ubergraph, that would immediately serve what Sabrina is asking about, really, because like you could just query for diseases that have either a in taxon or a present in taxon link to whatever taxon, and that ought to work. So that would be one way to do that. Yeah, I don't know. Make an Ubergraph issue. I mean, that I think of. There are other knowledge graphs, but that's the one that I work on. So that's where I would go with that.
Thank you so much, Jim. And if you can upload, if this ontology you used for generating your examples exists as an actual OWL file, then I think it would be super cool to just upload it into the resources directory if it exists, so that people can play with it if they want to. And yeah, if you want to make remember to make the NCBI taxon issue just quickly and assign it to me, and then I will make sure that it's assigned to someone else about adding the missing constraints into the disjointness file.
All right.
Excellent. Thank you so much.
Great. Yeah, thank you. Thanks, everybody.